So, continuing in our quest for how to use a spectrophotometer effectively, we can extend the similar concept of inorganic chemistry, where we used to do the titrations. Now, can we do a photometric titration to the same accuracy with respect to volumetric analysis? In general, I think many of you are familiar with acid based titrations and then complexometric titrations, and then there are iodometric titrations, like that. Different kinds of titrations are there, precipitation titrations and all those things, and many of them you must have studied and practiced also in your practical classes during your college days. Now, is there something like photometric titrations also? The answer is yes. We can do photometric titrations using a spectrophotometer. What we can do normally is, if we assume that there is a substance A and it reacts with a colored reagent R, the complex will keep on forming. So, once the complex is formed, the color will not change. So, at the end of the titration, the absorbance will come to a standstill. So, that should be the end of the titration. So, basically photometric titrations are useful for locating the equivalence point of a titration, provided the titrant or the titrand or one of the reaction products absorbs the radiation. This is very important now. In most of the spectrophotometric titrations, either there should be color formation or there should be color disappearance. If any one of these are not there, then there is no case for a photometric titration. Basically, what a titration curve describes, it describes the plot of absorbance corrected for volumetric changes, because we are going to add some reagent, and so it is going to increase the volume of the titrant, and it should be plotted, absorbance should be plotted as versus the total amount of reagent, that is concentration of the reagent. The end point normally is obtained by extrapolating the linear portions of the curve, because obviously it is not possible for us to end exactly at a particular point. So, what we do is we normally extend the linear portions of the curve, and the intersection we take it as the end point of a reaction. So, what is so great about this? The answer is the photometric titrations are normally done at ppm levels, parts per million, milligram per liter level. Okay. Whereas, normal titrations, what you are familiar with, are done in milligram quantities, that is 1000 times higher concentrations than spectrophotometric titrations. That is the biggest advantage. Then there are other advantages also, which we will see later, and sometimes photometric titrations can be automated. We can have a ready-made recorder. So, even if you shoot the end point, still you should be able to pinpoint the end point later. That is another advantage. Third is, you can record the first derivative, second derivative absorbance also. So, that is also very important with respect to the analysis of amino acids. So, look at it. Now, how does it look, a photometric titration apparatus? This is the picture of a photometric titration apparatus. On the top I have shown a spectrophotometer and attachment, tungsten lamp here, and a tungsten lamp here and a photodiode detector here. What happens from the tungsten lamp? The radiation falls through and then the reaction is taking place. Here the path length and then the absorbed radiation, the height of the sample is the height of the beaker. So, the radiation will pass through like this, reach a mirror or something like that, and then again travel through the same distance. That means path length will be doubled and then it will reach the detector. So, for a given absorbance, for a given solution, the path length is always double in this design. It need not be necessarily in all designs. Okay. We have some amount of filter and other things also here. If necessary, we use them, otherwise for a given wavelength the photometric titration should be possible. Very comfortably one can do the titrations. So, here are some of the titration curves, typical titration curves where we plot absorbance versus volume of the titrant. So, in this case you can, in the first case where I am pointing the pointer, we can deduce that the absorbance is constant here, that means there is no reaction. After some time, when all the reactant is consumed, there is going to be some sort of a color complex formation, and the color complex formation keeps on increasing, and the titration end point of this would be obtained by extrapolating the straight line portions of this, very simple this thing. So, in this case we can conclude that the reaction product is colored and the reactant is not colored. So, absorbance remains almost constant. So, until the minimum complexation point is reached, there will not be much change in the absorbance. Sometimes what happens is there is a certain amount of color keeps on forming. So, this is a part B is another type of reagent where absorbance keeps on forming, and once all the reagent is all the titrant is used up, the addition of the chelating agent or coloring agent will not increase, because there is no more metal ion to be reacted. In that case what happens, the absorbance of the substance complex in the titrant will remain constant. So, part B is where the complex keeps on forming, but once once one of the component is used up, the absorbance will become constant. So, the intersection of these two, this portion as well as this portion, this is the intersection point, that is where we have to conclude that the equivalence point has occurred. And once you get the equivalence point, it is very simple, N1 V1 is equal to N2 V2, that kind of reaction you can calculation you can always go ahead. Now, look at volume, look at the third picture C. Now, here what is happening? The absorbance is very high in the beginning itself. That means the titrant is a colored substance. I keep on adding a reagent and the colored substance keeps on losing the color, decomposes, and then once all the material is used up, the reagent color which is colorless will maintain the absorbance constant. So, for highly colored substances, this is the kind of photometric titration curve you will be expecting in this case. Now, look at D. Here there is certain amount of color formation and also there is additional color, because if it was only one type of complex, it would have reached like B, you would have got a curve. Now, here what is happening is I have a first equivalence point. After that there is one more equivalence point, it is forming another complex, say a mx2, this is mx1, this could be mx2 or something like that, which is also having same absorbance lambda max, and then it keeps on increasing until you get a end up with a curve like this B. So, I have not drawn this third part. So, you can see that in this case there is a formation of second complex also with the same reagent. But here you can imagine that the absorbance remains the same, that means both complexes are of the same color. If both complexes are of the same color, you will end up with a curve something like this. Now, imagine I have two complex, one is color complex, but after reacting with a reagent, it is forming one more complex whose lambda max is different. Okay. So, the absorbance keeps on coming down, at some point it reaches minimum, and then you will see the formation of some other color, and if the lambda max of this part of the complex is very near to this, you need not change the wavelength. Okay. So, the same wavelength will keep on giving you increased absorbance. So, if you get a curve something like this, I would simply conclude that okay, there is a complex formation here, the complex is getting used up, the metal ion is getting used up, but at the same time another complex is formed which is almost of the same color, because I am not changing the wavelength, and then that complex color also keeps on increasing. So, this is a very typical reactions of several metal ions which are colored. For example, if you do any titration with respect to using chromium or manganese, the color will keep on coming down and the complex color will keep on increasing. So, suppose this is orange, then this is red, you can use the same wavelength to continue the titration, and once you finish the titration, you will be able to determine the equivalence point in this case. Now, here what is happening? There is an increase in the complex, complex is being formed, absorbance is increasing, and then the absorbance is decreasing, and then again it is reaching 0. So, there are two complexes are being formed, one is an colored complex, another is a non-colored complex. Very simple interpretations, and you have to remember that most of these reactions must follow photometric rules, where the absorbance can vary only from 0 to 2. Okay. So, the solutions have to be extremely dilute, and one has to be a little careful in interpreting the absorption, titration and titrant concentrations. You have to take into account the dilution effect. If you do not take dilution into effect, the analysis will definitely be wrong, and of course, it does not make sense if we do the analysis wrong without taking into dilution. Even in normal titrations in your day to day, in our day to day experiments, what we do is we take the dilution, the very dilute solution in the conical flask and concentrated solution in the burette, so that the actual volume change, if not corrected, should be at least negligible. So, that is what makes the difference between normal titrations and such titrations. Now, this part A, this one is I am giving you an example for this curve. The example is arsenic 3 with bromate bromide. Here what happens? Initially arsenic is colorless, it will react with bromate and bromide mixture, forming arsenic bromide, and arsenic bromide is colored. So, absorbance keeps on increasing. Now, second one, copper with EDTA. So, copper forms two types of single complex with EDTA. Initially copper is colorless. I am saying colorless because it is not necessarily colorless, need not be colorless, but the quantity of but the concentration of copper is so low, it will be in ppm level, you will not be able to see any absorbance here. So, I am saying it is colorless, but copper EDTA complex is colored. So, EDTA will keep on giving the increased absorbance until it reaches the equivalence point. After that, any addition of EDTA, which itself is colorless, cannot increase the concentration of the color, or copper cannot increase the absorbance. So, reagent is colorless, but reactant is colorless, but the complex is colored. So, there will be an increasing curve attaining a constant value. Now, the third one, paratoluidine in butanol with perchloric acid. Here paratoluidine is a very simple chemical which is available in almost all the chemical shops. It is used for the determination of chloride in swimming pools, very normal reagent. So, this is third one, paratoluidine is colored and perchloric acid is colorless. So, the color keeps on coming down, and then once all the paratoluidine is used up, the concentration of the color of the same reaction mixture remains constant or colorless. So, very simple example of such a reaction. Now, look at the fourth one, colored titrant reacting with a titrant to produce colored product absorbing at the same wavelength. Now, the next one is this one, bromination. So, initially the bromine is colored, the sample is not colored, sample is colored, bromination, it keeps on coming down. Once the bromination is there completed, the bromination the brominating reagent itself is colored. So, absorbance will keep on increasing. So, this is the another type which we have seen, and formation of two successive complexes. The last one, which is very easily understood, one is colored, another is not colored. So, different types of titrations can be conducted using the photometric titrations. So, advantages of a spectrophotometer using a photometric titration involves the ppm level. Once again I am reiterating, ppm level analysis, no danger of overshooting, because anyway we are going to overshoot the end point. Exact equivalence point cannot be reached by manually, you have to draw the curve and then extrapolate, and the reactions will be extremely accurate to the point of about 10 raised to minus 3 or minus 4 molar concentrations. Very few titrametric methods are available for titrametric determination of compounds and organic things, organic compounds at 10 raised to minus 3, 10 raised to minus 4 molar concentrations. Then another aspect we are going to discuss now, that is the kinetic methods. In kinetic methods, what is important? The reaction should continue and you would like to know the rate of a chemical reaction. So, the rate of a chemical reaction can be followed if one of the substances is colored. So, all you have to do is make the reaction, take out a sample from time to time and determine the concentration, how much is consumed or how much is produced, like that, as a function of time. So, then you can plot the chemical rate equation and other things. So, the actual measurement, suppose you have a spectrophotometer and put your reaction mixtures in a cell, okay, and just relax. Ask the computer to measure absorbance every 5 minutes or every 1 minute. So, it will keep on giving you a number of absorbance readings versus time, and that is it basically. So, we get a dynamic chemical method before attaining equilibrium time. Once equilibrium is attained, there will not be any change in the concentration, and which in turn means there is no change in the absorbance either. So, a variety of chemical reactions can be characterized by spectrophotometry. In fact, spectrophotometry has become one of the most important technique to determine the kinetics of a chemical reaction, and there are several examples where you can follow such reactions spectrophotometrically. Now, here you can see the determination of trace quantities of iodide in this reaction. For example, 2 cerium, and cerium will react with arsenic. This is a catalytic reaction. Cerium will get reduced to cerium 3, arsenic will get oxidized to arsenic 5. This reaction proceeds in presence of iodide ion. Now, the cerium is slightly yellow colored, arsenic is not colored, but iodide cerium 3 is not colored, I think. Cerium 4 is colored, cerium 3 is not colored, and iodide ion is not colored. So, by following the change in the absorbance of cerium 3, you can determine the kinetics of the chemical reaction. Similarly, there are other examples. Several enzymes act as catalysts. So, such reactions can be followed by photometric titrations. Then there are determination of the ascorbic acid in phosphomolybdenum blue method reaction. All these things are quite simple basically, but you should know the chemistry of the thing. I will not be able to teach you all the chemistry that is required in this course, but in general what is expected of you is to know the chemistry. Then what you are learning here is the instrumentation and applications, potential of the applications, etc. And that is what I am trying to highlight here. Okay. Now, this is how your chemical reaction will look like. If you plot initial rate change of dP by dt, concentration change, and then this is the concentration of the substance, you will end up with a curve like this. So, dP by dt minus K2E. So, there is 1 K2 by Km general reaction. I have written a general reaction here, and this is a mixed order. It is not a single order, it is not first order or second order, but in a mixed order reaction. So, very simple example for enzymes. This kind of curves are available in the data section of several databases, and you can look up the methods for such reactions. So, kinetics methods can be basically classified into 2 types. One is the differential method that computes the rate of chemical reaction from the slope of the absorbance versus time. I relate it to the analyte concentration, that is one thing. Integration methods are also there. In integration method, what we use is the integrated form of the rate equation and determine the concentration of the analyte from the absorbance changes that occur over various time intervals. Of course, we need to use curve fitting methods to fit a mathematical model for first order reaction, second order reaction, third order reaction or fraction order reaction. All these things are quite possible, but what is important is you are measuring the absorbance versus time curve, and other parameters can be computed from the model, including the analyte concentration. That is what is important in chemical kinetic methods. So, kinetic methods based on the reactions with half lives greater than about 10 seconds, such reactions are classified as fast reactions. So, they are also they are also amenable for spectrophotometric follow up. So, temperature control is very important in such cases, because we know that any chemical reaction is temperature dependent. So, it is very important for us to maintain the reaction mixture temperatures up to plus or minus 0.1 degree centigrade. So, you have to have a jacketed reactor in which the samples are put, and there should not be any heat changes in the reactor. So, the whole thing must be jacketed with cold water circulating. Many reactions are exothermic and some reactions are endothermic. So, all such fast reactions, exothermic and endothermic reactions, must be very carefully selected and studied using temperature control. In several commercial instruments are nowadays available, as you know, the one can they are dedicated kinetic measurement instruments. So, they will give you an optional switch in the machine, whether you want to make absorbance measurements, transmittance measurements, and then concentration or kinetic methods. So, there are automatically the program will take over the kinetic methods, then it will ask you at what time you will be able to, you should measure the absorbance. So, you have to feed in all that data whenever you want to use a kinetic method, develop a kinetic method and try to determine what is the order of the reaction. So, for reactions with half lives of less than 10 seconds, again what we can do is we take the reaction mixture and cool it immediately, that is stopped flow reaction. You can bring it to room immediately room temperature or cool it immediately, or you can mix this, stop the flow, and the stop flow mixing technique is very effective, especially with half lives of the reaction if it is less than 10 seconds. So, this technique in this technique what happens is reagent and sample are mixed rapidly and the flow of the mixed solution is stopped downstream suddenly. So, the reaction is then monitored. So, remember all these things are meant for the fast reactions, kinetics, and if it is a very slow reaction, there is no problem at all. You know, you can determine the every 5 minutes, 10 minutes, if you want to measure the absorbance and determine the concentration, there is absolutely nothing that can stop you from doing so for thousands and thousands of chemical reactions. So, another aspect, that is composition of a complex. Quite often we want to determine, we want to know what is the composition of a chemical substance. In chemistry subject, we define elements and then compounds and then mixtures like that. Similarly, any chemical reaction that undergoes a transformation using a complex reagent is known as it is known as complex reaction. So, basically complex reactions are carried out using high molecular weight reagents and these include ethylene diamine tetraestic acid, nitrilotriestic acid, and several organic reagents and several other there is a vast literature of coordination chemistry where complex reactions are carried out. And one of the aims of a complex reaction, important aspect of a complex reaction, is to find out what is the combining ratio of the complexing reagent and the element. Okay. Now, this complexing reagent can always be determined by titration and other classic techniques are there. You can do the titrations, you can do gravimetric analysis and all that, but spectrophotometrically again it is a very beautiful technique to determine the combining ratio of the reagent and the metal ion. And there are approximately 3 to 4 several methods, but 3 are most popular, and these include the method of continuous variation, and another is a mole ratio method and the slope ratio method. Technically they look very intricate, but in actual practice most of these things are quite simple. For example, we can take a look at one of the methods of method of continuous variation. It is not something new, because you have already seen a curve of that type in the photometric titrations. So, method of continuous variation is very simple. This is the mole ratio method, and continuous variation method is essentially the same. This is Yo's mole ratio method, but method of continuous variation I have not shown you in this figure, but maybe I will give you an assignment regarding the continuous mole ratio. Basically it is nothing much. You take the two reagents of the same molarity. One is your reactant and the complexing agent, and keep on mixing until the composition absorbance of the complex reaches constant. It will be something like this curve B. So, if the molarities of the reagent and the complex are same, you will end up with a curve something like this, and where the inflection point occurs, it is the you can determine the volume, and this volume is known, reactant volume is known. So, if the molarities are same, you can determine whether it is 1 to 1 or 1:2 complex, etc. And then we will look at the other two methods, that is composition of a complex, that is Yo's mole ratio method, or the Jobs this is the Jobs method. Okay. So, this we will continue our studies in the next class. So, thank you very much. Have a nice day.